Hi, my name is Prakash Mitra, and this is my Physics 2211 Lab 5 Slinky drop. Purpose, main idea. So the purpose of this lab is to investigate the behavior of a stretched slinky when released from equilibrium. The purpose of this lab is to analyze and compare the motion of the falling slinky with both an experimental and computational model. We will be using Tracker to obtain the observed motion and use GlowScript to create the computational model. So some fundamental principles and equations we'll be using in this lab is Newton's second law, which states that net force is equal to mass times acceleration, or that the net force is equal to the change in momentum over the change in time. We'll be also using the velocity update formula, which is the final velocity is equal to the initial velocity plus the net force divided by the mass times delta t. We can also use the position update formula, which is the final position is equal to the initial position plus average velocity times delta t. And also the force of gravity, which is negative mg in the y direction, and also the drag force, which can be calculated by negative b, which is the drag force constant, times v squared times v hat. So some assumptions and conditions we assume in this experiment is that we're assuming that the forces acting on the object to be gravity, the tension force throughout the slinky, and the drag force acting on the slinky. And the object only moves along the y direction, especially in the negative direction, and the system is the slinky, and the surroundings are everything else such as the air and the ground. And this is the tracker data that I use. So in doing this tracker experiment, I first set my origin to be the bottom of the slinky as I'm tracking the position of the bottom of it. And I set the calibration stick to be the height of the person. And then I used the point mass to track the bottom of the slinky over the course of the video. So this is my GlowScript code. So as we can see on the top left are all of my constants I set. So I found the mass of the slinky to be 0.205. I set the position and velocity to both start at rest and start at the origin. And I used the increment of 0.005 as my delta t. And I found after some trial and error that my drag force constant was 75. And so I have two while loops here because the experiment can be broken up into two chunks, where the first chunk is when the top half of the slinky converges onto the bottom half, and then the second half of the experiment is when the whole slinky moves together as a whole to the ground. So overall, that whole thing took 0.516 seconds, which is why the maximum time condition is 0.516 seconds. And the first time condition was 0.308 seconds, which is how long it took for the top half to completely converge onto the bottom half. And so I calculated net force using the two forces at play, gravity and tension, and I update the velocity and position of the slinky as needed through the appropriate formulas. And in the second part, the forces that are in play are gravity and the drag force, and the net force is calculated appropriately, and the velocity of the slinky and position of the slinky are updated appropriately. And this is the graph that I got after using my computational model and merging my experimental model into a graph. And so we can see that the computational model actually predicts the slinky to drop later than the experimental model did. As we can see, the experimental model is trending to reach the bottom quickly or faster than the computational model, which is in blue, and the experimental model is in red. Some sources of error that may have happened is that incorrect code may have been typed, or there may have been slightly inaccurate initial conditions that I typed in the code. Also, when using to track the pointer locations, I could have picked like unprecise locations of where exactly the mass was, or the bottom of the slinky was. And also, outside forces such as air resistance may have slowed the mass down over time, which means there's work done by the surroundings. And also, the drag coefficient may have been incorrect. So what does it mean? Does the bottom of your model stay stationary? So the bottom of the slinky remains stationary due to Newton's first law, where an object at rest stays at rest unless acted upon by external force. This is because the gravity force and tension force are equal in opposite directions, which results in a net force of 0, which makes the bottom of the slinky stay at rest. So what if the gravity in this experiment was less than the gravity of the Earth? Would the bottom still stay stationary? The motion would not change, as the tension will always be equal to negative Fg. Thus, if the gravity was less, there would be less tension, so the bottom will still stay stationary. So in summary, I found that the bottom of the slinky does stay still until the top of the slinky comes down onto it. For the first part of the experiment, the only forces acting on the slinky are tension and gravity, and the second part have forces of drag and gravity acting on the slinky. Also, the computational model predicted slinky to fall to the ground later than the experimental model. And yeah, that's it. Thank you.